then click that off with our alcohol group so that our net reaction is favorable. But when we draw that cute little ATP becoming whatever, it's involved. You're going to be drawing arrows to it. It's part of the reaction. So that's all I have to say about that, and pointing it out again and again. You'll see that example a lot. Everyone loves glucose 6-phosphate for some reason. So that helps us for almost all of our reactions. Almost every reaction you'll ever see, you can express in delta G, you can do all that stuff. I do want to point out there's one other type of reactions that happen. Redox. We see redox reactions pretty commonly in biochemistry, and I want to remind us about them and give us a perspective on them. So, clear your mind of all thoughts. I think that happened about an hour ago. Zing. Here's an example of reaction. Lactate turning to pyruvate, plus 2 protons, plus 2 electrons. We got these electrons involved. We're changing the oxidation state. So let's remind ourselves of our little Gen Chem here for a second. Going from the left to the right, are we oxidizing lactate or reducing it? Oxidizing it. How can I tell?
Losing electrons.
Ooh, losing electrons, creating more bonds to oxygen. I liked both of those answers. What's the cute little mnemonic they teach these days? Oil rig. I hate you, oil rig.
Is like tiger goes grr or something?
Yeah.
Yeah.
Leo. So here's the deal.
Leo goes here.
I never heard it until once. I was like, what?
A lot of, for whatever reason these days they teach oil rig. I hate it, and I'm going to show you why. Because I'm petty, is the short answer. I learned Leo the lion goes grr.
Same thing.
I know.
No, but it's not.
I
And here's
know,
why.
I know.
No.
No, I said tiger.
Tiger.
Oh,
I
tiger,
was like,
yeah,
tiger
that
goes
would
grr,
work.
and he's like, it's Leo. And I'm like,
Yeah.
whatever.
Notice, so this one says loss of electrons, if I could spell electrons, is oxidation. This one says oxidation is loss. Of what? Hair? Loss of petunias? It really should be oily regi. And until they teach oily regi, I'm going to claim Leo Gurr is better. So, like, you're kind of dropping the ball here, right? This is all about electron transfer processes, and you forgot to mention electrons? It's dropping the ball a little bit. I'm not impressed. I'm not. But again, yeah, we're having this loss of electrons. Electrons are coming off of here. How do I know it's 2? How would I figure out that this structure versus this structure was 2 electrons different? I hear this little like count them around the carbon thing. No, that's good. I wasn't trying to make fun of you. I'm saying that's good. Say more. Someone in the back. How would I figure out the electrons here? How many electrons does this carbon have? How do I do that? There's no wrong answers. This is a safe place. Yeah, we're going to count bonds. I like that. Let's do it. So I'm going to redraw that one right over here. There's my little central carbon there shown in pink. When I have a bond between a carbon and a hydrogen, where does most of the electron density reside? Carbon. I could draw this as a cute little like reverse teardrop. Why? It's more electron negative, right? So these 2 electrons in this shared bond are mostly with the carbon. I'm going to be like, the carbon. Ooh, now he's got a mustache. I'm going to say the carbon owns them. What about the 2 electrons between 2 carbons? Shared. But I don't like sharing. So let's say they each own 1. Now it looks like 2 Pac-Man kissing. They each own 1 electron. Carbon to carbon, another pair. Each own 1 electron. Carbon to oxygen, where is those electrons going to be?
Oxygen.
On the oxygen. So carbon gets none. Womp womp. So how many electrons does that carbon have?
4.
4. Does that make sense to everybody? So as biochemists who are lazy reckon it, this has a reduction state or an oxidation state. Let's say oxidation state to make our life easier. An oxidation state of 4. Let's do the same game to this guy. Carbon to carbon, how many does he keep? 1. Carbon to carbon, 1. 2 electrons. Carbon to oxygen, how many does he keep? 0. So he has 2 electrons to his name. This poor carbon has an oxidation state. Yeah, he's electron poor, an oxidation state of 2. So we went from an oxidation state of 4 electrons to an oxidation state of 2. We lost 2 electrons along the way. Woo! Kind of fun, huh? So fun. In biochem, these are always going to be paired. You're not going to actually have free electrons going wandering around. This is an incomplete reaction because those electrons have to go somewhere. Very typically in biological systems, where they go is to an electron acceptor called NAD+, which will then become NADH. It actually accepts these guys too, because it becomes NADH plus a proton. So if you're wondering where that H magically came from, it's one of these guys. So NADH is going to couple into there and grab those guys. And we can do redox reactions. And I have a little summary on the next page of how to calculate oxidation states if it's been a little while, with cute little Lewis dot structures. So for the pink carbon in each of these, it lists the oxidation state, all the way down to carbon dioxide. Wah, wah. But I want to point something out to you that makes this all much more important to me. Redox is really the process of human digestion. That is, we eat sugars, which look like this. Sugars have a lot of alcohol groups, and we turn them into CO2. Or if we need something that's more high in energy, that has more staying power than sugar, we eat fats, which look a lot like alkane chains. Why is fat more calorie dense than sugar? Because it has more electrons. And the whole goal of human digestion is to get electrons. That's why fat's more calorie dense. It has nothing to do with physical properties, or it has to do with electrons. Calorie dense, electrons. We're little fleshy, squishy robots. We like electrons. So, just a reminder of that. Good stuff there? Okay. Here's the last bit that I want to mention so that I can check a box you've seen it, but just to be clear, you will not need to know this on the test. Do not waste your precious limited brain power memorizing this. If you, yeah, exactly. No, so here's the thing. When there are redox reactions, instead of giving you a nice convenient delta G, if you look up online a redox reaction, they will instead give you a delta E, which is the standard reduction potential. And instead of being given in kilojoules per mole, it is given in volts. And that's annoying. But luckily, it's really easy to convert. And again, you do not need to memorize this, but I do want you to know it's out there as a tool. So if you ever find a problem where this would help, this tool exists. And it was defined by Faraday. And he said delta G equals negative N, which is the number of electrons. Number of electrons. So for example, in this process, N would be 2. Negative N times the Faraday constant times the delta E. So it's just a scaling factor to convert between delta E and delta G. Good so far? And again, you could look this up. The Faraday constant is 96.5 kilojoules per mole volt. Kilojoules per mole volt, 96.5. So if you had some reaction, you could convert back and forth. Some years I've spent some time on this. I don't think it's worth your while right now, so don't memorize it. But let me just point out one thing that I think is kind of neat to kind of put that in perspective. If we then say we have this relationship, I could convert from delta G into an equivalent amount of volts, into a voltage. So let's take my good old friend ATP. Why not, right? ATP is a bond formation or breaking. It's not actually redox, but it's a bond, so let's pretend that's 2 electrons, because a bond is 2 electrons. So I've got negative 30.5 kilojoules per mole equals negative 2 times 96.5 kilojoules per mole volt times delta E. So divide that out. Negative over negative is a positive. So in terms of volts, what is that, like 0.25? That was just off the top of my head. What is it actually? Let's see, that's about 200. 30 divided by 200 is, yeah, like 10. 10.3. Right? Did I do that right? Wait, that doesn't seem right.
Sure, it's like 0.58.
Yeah, that didn't seem right. Negative 30.5 divided by,
But that should be positive.
it should be positive.
It's positive.
0.158
I'm
volts.
sorry,
There we go.
I thought it's negative 2.96.
Oh, 2 times 96. There we
Yeah,
go.
that's what it is.
Yeah, about 0.16 volts. The reaction that drives the human body is about 0.16 volts. Next time you get your 2 volt AA battery, that's pretty strong energy storage, right? The little alkaline reaction that goes on in your AA battery is like 10 times the strength of ATP coming apart. That's nice. Do you have a question?
Yeah, I know you can't interchange delta G naught prime with delta G, so is delta E naught prime the same as the delta E in the third?
Yeah, sorry. You would have to have these match.
Okay, sorry.
Yeah, no. That's not a bad question at all. You would have to have these match. Either both be under standard or both not be under standard. So thank you for clarifying that so I didn't mislead. I appreciate it. So again, don't dwell on the redox stuff. When and if it becomes necessary in class, we'll throw it at you and I'll remind you of this. Don't memorize it. But I just want you to know, if you ever see a value in like 0.78 volts, what the heck? It's just another way to express delta G. Just have to convert it. So that's the message. Let's take a much needed late 5-minute break, refresh our brains, get some water. We're going to change gears a little bit. It's good times, great oldies. Cool 105. Water. Awesome. Do you play?
Yeah.
Who do you play?
Mainly Reaper, but
Oh, you're my wife.
I'm a little.
I can't stand Reaper. No offense.
Who do you main?
Symmetra and Diva.
Okay. I'm sort of a flex for Diva too.
Yeah.
I flex a lot.
I'm a Diva. Yeah, oh yeah, and I flex Reinhardt. When
Yeah.
I'm playing competitive, I mostly play Reinhardt.
Yeah.
Josh, what's going on, man?
But it raises my blood pressure because I start screaming, get behind the rectangle!
Oh,
Oh
I've
my
seen
God.
Just
You
get
play
behind
so
the
dumb.
rectangle!
from everybody.
Yeah, I accidentally with Josh and one.
Like, I play like everything. That's kind of nice.
Yeah, I just didn't want to.
Yeah, addictions,
Yeah.
it's a thing.
I wanted to ask,
Yeah.
this,
Getting it? Yeah. So we were at pH 7.4. That's outside. Yeah. Yeah.
I still wasn't like every time. And I like tried to rearrange it, do just the denominator.
Yeah. 0.029 squared times that jazz. 10 minutes. It should just be 1, not 7.
No, that's perfect. Just doing it.
Yeah, probably. Yep. Yep, that was what was doing it. Oh, math errors. What's up? Okay. Sure.
I need to get it.
Oh, yeah, no. I get it. No, like I said, this is a part where like oh,
Yeah. For some reason,
yeah. So, if you can email me, I'll remember better than just write it down. But let me give you the short version. You can always get to the right answer from this equation.
Yeah, I just don't know. I get, that's what I'm doing. Like I get the equation, but like when you were showing like the glucose,
Yeah.
numbers,
Where
I'm
to
like,
check it.
okay,
Yeah.
I get the equation. I just need to
Build with
from,
it. Yeah.
from
No.
numbers that are
I
not
definitely have
great.
some resources I could send.
Maybe not.
Yeah. Shoot me an email and.
All right, I'll do it right now.
Yeah. Just so it doesn't leave my head. Who are you again? I know.
I know. God. I was your first.
Well, I work here every day. Remember my Wi-Fi.
You know what I mean? You know what I mean?
You know what I mean? It's terrible. I say it like that. Did you really do it? Oh, I just watched it. Not in the meeting, there might be, but still, I don't know what, yeah.
What you mean about in the mean?
Those are really bad.
I'm being serious, deadly serious.
Really, it's just like easy.
All right. Stretch. Oh.
I don't have lecture.
Yeah, and we're reading also. All right, challenge question while we're waiting for the last few people to come back in.
Tell me about it.
Challenge. So we have 3 partial reactions up here with 3 different delta G naught primes. Here is the overall equation, and we're trying to figure out its overall delta G naught prime. This one was ripped out of a GRE question. Biochem GRE.
I know, right?
No.